So in today's lesson, what we're going to be talking about are acids and bases. So much of this lesson should be a review from grade 11 chemistry, but it's well worth reviewing because it will play an important part in the acid-base equilibria section of this unit that we're going to be looking at. So in chemistry, there are a few different ways that we define an acid and a base. And so today we're going to review two of them. And the one that we tend to think of from our grade 10 time was this Arrhenius definition, which is an acid is essentially a substance that when dissolves in water will either release hydrogen ions or produce hydronium ions. So let's just review this process. So for instance, if I had HCl, which is like, hydrogen chloride is a gas, and I dissolve it in water, then what happens first is I have this hydrogen chloride that will dissociate, right? So I have this and this, I've got my hydrogen cation and my chloride anion. But what immediately happens in water is that hydrogen ion is going to combine with water to produce this hydronium ion, right? So again, I've got an extra hydrogen, which gives me 3 hydrogens in total. I'm taking a substance with a +1 charge and adding it to a neutral substance, giving the new substance an overall +1 charge. And that particle that's produced is called hydronium. So if we're talking about an Arrhenius base, then you'll think, people tend to think about the hydroxide ion in association with alkaline substances. And that's in line with our Arrhenius base. So a substance that when dissolved in water releases or produces hydroxide ions. So our strong bases, like sodium hydroxide, for instance, when dissolved in water, will dissociate to produce hydroxide ions and whatever the cation is that's associated with that, right? So just the sheer presence of that hydroxide ion and that compound that's releasing it and producing it in solution, that is in accordance with the Arrhenius definition. However, there are other definitions that are worth considering and are extremely helpful when we're considering equilibrium systems. So I want to review with you the Bronsted Lowry definition. So the Bronsted Lowry definition is a substance that in water donates a hydrogen ion, which I will refer to as a proton, whereas a Bronsted Lowry base is a proton acceptor. Okay, so let me remind you why it is that hydrogen ions we will call protons. So if you look on your periodic table, a hydrogen ion has a mass number of 1 and an atomic number of 1. And so what that tells us is that, if we were to draw a Lewis structure of our hydrogen ion, we would have, of our hydrogen atom rather, we would have our nucleus with a proton in it, 1 proton, right? Remembering that number there refers to the number of protons and the number of electrons, right? In a neutral atom, of course. Now, since I can see that my mass number and my atomic number are the same, that tells me is that hydrogen has 0 neutrons. So the only thing I have in that nucleus of my hydrogen atom is that 1 proton. And so then I'm going to draw in its electron. And there's its electron. Here we go. Okay, so now if I want to talk about H+, conversely, to form an H+ ion, a hydrogen ion, what needs to happen to my hydrogen atom is that it needs to lose that 1 electron that it has. And when that happens, then really I have, this whole shell completely gone. And when that happens, all that I'm left with is in fact my nucleus, which only contains a proton. So that's why we say that a hydrogen ion is the same thing. We can use those terms interchangeably in chemistry. Okay, so let's get back to these definitions of Bronsted Lowry and acids and bases. So if I'm looking at hydrochloric acid here. It's obviously going to be my acid, but in this case I've got ammonia as a base. And so it's immediately evident to me that I'm not really seeing any hydroxide there at all. Where's the hydroxide? It's a base, but how do I know that, right? And so let me kind of give you a breakdown of ammonia as a base on its own. And so here we go. Let me do that. So this is just sort of as an aside. So if I had ammonia combining with water, and I'm saying that it's going to be a base, then what I see happen is that ammonia as a base is going to be accepting a proton. It's going to be accepting it from water. And when it does that, I end up with ammonium. But then water loses a proton, and then I end up with hydroxide. So it's not obvious within my compound, my ammonia compound, that it's a base. But I can see that in an aqueous solution, it's going to definitely liberate hydroxide ions and give that solution a high pH. Okay, now back to this example that I've given here. And so what I'm seeing here is that what I'm looking for is I'm looking to see, well, how is it that I can see that hydrochloric acid is acting as an acid and that ammonia is acting as a base? Well, we want to look at our products and see, well, what happens to the hydrogen? There's only one hydrogen here and some 3 hydrogens here, but what's happening to the hydrogens when I consider my products? Well, what looks like has happened is that my hydrogen ion in my acid was donated to my ammonia, right? So in having donated its proton to ammonia, I end up with, I can say that my hydrogen chloride or hydrochloric acid has donated the proton and the ammonia has accepted that proton. So that is what makes hydrochloric acid an acid and my ammonia in this circumstance the base. Okay, so I want to review acid-base conjugate pairs. So when you look at a reaction involving acids and bases, if the acid is going to be donating a proton, it is going to be creating a base. And so that essentially creates what we call an acid-base conjugate pair. So acid-base conjugate pairs differ by 1 proton. So I can tell in this circumstance that ammonia and ammonium are acid-base conjugate pairs because it looks to me like there is 1 additional proton. Now, where did that come from? That came from the fact that this particle right here, my nitric acid, ending up donating a proton to my ammonia. Right? So in donating that proton, I end up producing ammonium. And then since my nitric acid has lost that hydrogen atom, I end up with a nitrate ion. Right? So you can see here that my acid-base conjugate pairs are ammonia and ammonium, differing by 1 proton, and nitric acid and my nitrate ion. Hopefully you remember that from grade 11 chemistry. Okay, now I want to add on to this a little bit because we didn't really talk about this last year, but it's going to make a difference in terms of how we look at equilibrium systems this year. So important for us to understand that a weak acid will have a strong conjugate base and vice versa. Okay, so and the stronger the acid, the weaker the base. Okay, so here's the exact same reaction that we just saw. And so I'm going to give you a little bit of insight, and soon enough you'll understand how I know this. But I'm going to tell you that HNO3 is a very strong acid, right? Nitric acid, you probably recognize that as being a strong acid. But its conjugate in this scenario is my nitrate ion. Since nitric acid is extremely strong, that would mean that my nitrate is a weak base. Okay, now I also know that my ammonia is a weak base. So what conclusion can I make about ammonium in light of that? Since ammonia and ammonium in this scenario are acid-base conjugate pairs, I can therefore deduce that ammonia is a strong acid. Okay, let's talk about water in all of this. So water is an interesting species because it can act as either an acid or a base, depending on what it is combining with. And that's because it has the ability to both donate and accept hydrogens, and it will do so based on what it's combined with. Okay, so in this case, what I've done is I've taken water and I've shown it as acting as a base and an acid, but let's show how, let me explain how this is showing this. So HCl I know is an acid, right? We know hydrochloric acid is an acid. So if HCl is my acid and water is my base, acids always donate protons and bases are proton acceptors. And so I'm going to show water as accepting a proton. And when it accepts a proton, then I produce this hydronium, right? The characteristic acid ion. Now, if I show it with ammonia, ammonia is a base. If I show water combining with ammonia, which is a base, then water doesn't have a choice but to be the acid, right? Because that base is going to accept the proton. And so my water being an acid is going to be the proton donor. When water donates the proton, what I end up with is my hydroxide ion as a result, right? My water minus a hydrogen ion is going to produce hydroxide. And as a result, I get my ammonium ion here. So there are substances like water that can both donate and accept protons. And I'm wondering if any of you remember what we call such species. Well, one term that we use is amphiprotic, sometimes amphoteric. Let's kind of break down that word. So amphi is a prefix that means like dual or both. Think like amphibian, both land and water. So amphiprotic, meaning it can both accept and donate a proton. So here's a typical example. Write a chemical reaction equations to show that H2PO4 ion is amphiprotic. Okay, so we're going to take this thing here and show that it can both donate and accept a proton. And in each case, we're going to identify the acid-base conjugate pair. So pause the video, give that a try, and then return when you think you've got it and you want to check your answer. All right, here's my solution. This is how I would go about this problem. I would react each species with water. So down here, I've got my H2PO4 with water acting as an acid, and I'm going to show it acting as a base. In an acid, it will donate a proton to water, forming hydronium. So if it's an acid, then I'm going to see it donating a proton to water. And when it donates a proton to water, I end up with my hydronium. Right? But as a result, and we want to be really careful about this, as a result, I'm showing that the species that is produced has one fewer protons and also one less positive charge. So let's just talk about that for a minute. So if I have I have a species like HPO4 minus with a -1 charge, and then I take away one of its positives, so I'm taking away a positive, right? Then that's going to give me -2, and that's where I'm getting this -2 charge from. Now conversely, what I have here is I have in the second example where H2PO4 minus is acting as a base, remember bases are proton acceptors. So it's going to accept a proton from water. And in so doing, water loses a proton and becomes hydroxide. That's what makes the solution basic, and why H2PO4- is acting as a base. But as a result, I end up with H3PO4. And so you'll notice that, I have one extra proton as a result of the accepting of that proton. And also my charge changes as well. And so we want to be really careful about, indicating appropriate charges. Again, I started off with a compound with a -1 charge. And then what I'm doing is I'm adding in a proton with a +1 charge to give me an overall neutral charge. So there it is, a quick review of defining acids and bases using both the Arrhenius and the Bronsted Lowry definitions. I'm talking about conjugate acid and base pairs and amphiprotic species. So I hope that that's clear, but as always, please reach out and ask questions should you have any.